Welcome back to the second half of the indoor PM workshop. Thank you. Those were excellent talks that we had in the first part, and I look forward to the next ones. With the first part focused to remind you outdoor sources and how they influence indoor. Now we're going to talk about indoor sources of indoor particulate matter. And so we have four wonderful talks for this part. And before I sort of introduce the first speaker, I just want to mention there's been questions about the recordings and slides. Yes, they will be made available in the near future. The other thing I want to remind people about when we go into the panel discussion at the end, for today, we'll have all 7 speakers come back. So for those of you who have burning questions that we didn't get to, we'll have a chance to have a big, broad discussion of indoor and outdoor sources together. But I also want to remind people that the topics we're really focusing on are indoor sources and outdoor sources. There were many questions in the first part about health effects. To remind you that we'll have a special workshop just focused on health metrics and health and metrics on the 21st. And on the 28th, we'll have a whole session dedicated to mitigation. There are lots of questions about how do I clean my air, and we're saving those for that discussion. So just reminding you, this is a 3-part session and we will get there, but today we're focused on sources. So with that, it is my pleasure to introduce Nina Vance, who is an assistant professor and the McLaughlin Family Faculty Fellow in the Department of Mechanical Engineering at University of Colorado Boulder. And Nina is going to tell us today about fine particulate matter emissions from cooking. Nina?
All right. Thank you very much, Kim. Oh, I think need to move some things around here, just a sec. Okay, my name is Marina Vance, and I'm here to talk to you today about fine particulate matter emissions from cooking. So there are many sources of indoor particulate matter. Cooking is a very important one of them, and it can vary drastically from one home to another. This means that 2 homes in the same neighborhood right next to each other could have inhabitants with very different PM exposures. And for the context of this talk, I'm going to say that there are 2 air pollution components from cooking activities. First, the heat source that you use to prepare your meal, and second, the food itself. Primary emissions from cooking can include particles, volatile organic compounds, nitrogen oxides if combustion is involved, and a variety of other pollutants. My talk today will focus on fine particulate matter, particles, as that is the focus of this workshop. So here I present some classic examples from solid fuels, such as coal, wood, charcoal, dung, etc. Crop residues are also used, all the way to gas and electric, which may include an electric heating element, as you see here, or this induction cooktop, as you see here. And although solid fuels are of extreme importance globally, with almost 3 billion users worldwide and leading to almost 4 million premature deaths annually. This is data from the Global Burden of Disease study. It was estimated for the year of 2010. This is very important, but my talk today will not focus on solid fuels. Rather, I will talk about the most common cooking modes in developed countries, specifically gas and electric. So gaseous fuels could incorporate propane, LPG, natural gas, biogas, etc. When using cleaner fuels like these or electric sources, the food emissions themselves end up becoming important and must be investigated. So let's talk a little bit about the fate of indoor cooking emissions. There are primary emissions that may quickly be released during cooking, grow into a specific particle size, and then move through the indoor environment, where these particles might uptake semi-volatile organic compounds from building materials and from other sources. The volatile fraction of cooking emissions might undergo reactions indoors, could lead to new particle formations or other things. A large fraction of indoor PM from cooking and other sources is likely to deposit on indoor surfaces. And all of this will end up affecting the exposure and the health effect of the residents or the indoor inhabitants in this home. And of course, later, some of these emissions may find their way outdoors, where they might undergo atmospheric processing. The volatile components could lead to secondary organic aerosol formation outdoors. And in the end, it might impact ambient air quality as well. In this talk, I'm going to focus on each of these boxes that you see inside the house. So first, let's go over primary emissions. Let's jump right in with this comparison figure from different activity types from the home chem study. A lot of the results that I'll be presenting today came from home chem. So what you see here is a 5-panel figure. All right. Let's start with the bottom panel showing a ventilation experiment day. So these are time series of size segregated PM mass. The different sizes are shown by the different color lines. So on this sequential ventilation experiment that you see here, every time you see a green bar, the house was completely opened, all doors and windows, to allow maximum penetration of outdoor air pollution. And what you see here is a lot of coarse mode particles. Those are the black line, PM10. Come into the house, leading to indoor concentrations of maybe 5 or 10 micrograms per cubic meter. Well, this looks very different from the upper panels where cooking activities were performed indoors. You see here on the second from the bottom panel where a stir fry was cooked 4 times throughout the day, here, and here. And you see intense peaks of emissions. You can see from the y-axis getting to hundreds of micrograms per cubic meter of particulate matter. The same was true for a layered day, which is supposed to be a more representative, experiment simulating a normal day in the life where somebody came in and cooked breakfast, then they did some cleaning, no particles were emitted, then they cooked lunch, you see the particles, this is toast, tiny little peak over there, dinner was cooked and more cleaning. So again, hundreds of micrograms per cubic meter of particles were released in short spurts. And finally, at the very top panel, what you see here is an experiment called Thanksgiving Day, where volunteers came in the morning, they cooked the same breakfast meal as before, and then they spent the rest of the day cooking a Thanksgiving meal for 12 to 16 participants. Let's dig a little deeper on this Thanksgiving plot. So what you see here is that in general, activities that included things like browning, toasting, or charring of food led to higher concentrations of PM. This is nicely demonstrated by this big sharp peak here that was produced when Brussels sprouts were nicely roasted in the oven. Another thing to note about this experiment and the data here is that there is an orange line here showing that PM.1, so ultrafine aerosols or particulate matter 100 nanometers in size or smaller, were very high, reaching almost 100 micrograms per cubic meter in concentration at some specific times of the day. So this demonstrated it's not always true that ultrafine PM amounts to almost no mass, as is commonly said. In some moments in this particular experiment, the majority of PM 2.5, as you can see here, was actually PM.1. And for the rest of the day, the majority of PM 2.5 mass or total PM mass was actually PM.5, the red line. So this has implications on many things, health, exposure, but also on the use of low-cost sensors to evaluate air quality in these situations. So let's move on from this very specific scenario of, intense cooking to more normal cooking activities. In terms of specific meal preparations, we noticed that the meals that were prepared on a propane stove, shown on the left, led to about 4 times higher PM number concentrations than meals cooked by other means, like an electric hot plate or the oven or a toaster. Those number concentrations peaked and under 10 nanometers in size. In fact, the gas stove itself, which is a propane stove in this example, led to about 7 times higher concentrations than an electric hot plate, just by itself without any food. Once you add the food during meal preparations, those concentrations were much lower. There were fewer sub-10 nanometer particles. But the mass concentration, shown here on this part on the right side, remained basically the same. This indicates that the heat source might be responsible for the particle number concentrations, while the food itself might dominate mass concentrations. In terms of composition, multiple studies have shown that indoor cooking, as expected, leads to substantial amounts of organic matter, primary organic aerosol. But within organic, there is a lot of variability that could depend on the ingredients that are used, the cooking style, heat source, the type of oils, and other details. And specifically, the concentration of PAHs, or polycyclic aromatic hydrocarbons, is associated with cooking emissions was highly variable, which can have serious implications for health effects. Okay, so that was primary emissions. Let's talk a little bit about SVOC uptakes. These particle emissions may uptake semi-volatile organic compounds after emissions. So what you see here is a plot from Lunderberg and colleagues from the Alan Goldstein's group at Berkeley. It shows a chromatogram for particle phase SVOC, semi-volatile organic compounds, and shows that SVOC from cooking, which is shown here in red and in orange, were present in particles that were emitted during the Thanksgiving experiment at HomeChem. But other things from the house ended up attaching to these particles as well. Specifically in purple here, you see some peaks for phthalates and adipates, which are known plasticizers and are widely used in vinyl flooring. And you also see a bunch of peaks here in teal for cyclic siloxanes. And these could be coming from the oven or other building materials. On a different study by that same group in a California residence during normal occupancy, Christensen and colleagues, they show that the total concentration of SVOCs was enhanced when indoor activities were being performed, especially cooking. And then they also show that of all the VOCs that were present during cooking, about 14% was in the particle phase. And when they were using the oven, the particle phase percentage grew a little bit to 25%. All right, these SVOCs and particles that are emitted from cooking may end up undergoing chemical reactions indoors. So let's look at a case study. This is just what you see here are 5 time series for 5 different experimental days during HomeChem. Starting from the bottom, let's look at the blue line here. This was a sequential mopping with bleach day. So every time you see an asterisk, the house was being mopped on the floors with bleach solution. And we didn't see any particle formation. There's nothing going on. What you see on the next lines were what we call the layered days. So the peaks that you see here in the beginning, they correspond to breakfast activity. The peaks that you see here in the middle correspond to lunch. And then the third series of peaks corresponds to dinner being cooked. And then there's a 4th series of peaks. What you see here is new particle formation that occurred during bleach mopping that happened after a chili dinner was cooked. So the same thing was not observed on the first layer day in black here at the end. And what was different on that day from the others is that a lasagna was made in the oven. This means that it's very likely that some VOCs that were emitted during the chili cooking dinner hung around in the air in this house and then reacted with some components of the bleach solution and that activity to generate particles that were very small, less than 30 nanometers in size in the house. Next, let's talk a little bit about surface deposition. Particles emitted from cooking are very likely to deposit on indoor surfaces. This has a very different time scale than the intense, short-lived air pollution emissions themselves, so it must be thought about differently. So what you see here is some data from Orr and colleagues from University of California, San Diego, Vicky Grassin's group. And if we compare the figure on the left, it shows cumulative size distribution, particle number size distributions for what was going on in the air. So the blue line is for Thanksgiving, very intense cooking event, lots of particles were present. And what's shown in the red is for a stir fry, so fewer particles were present. However, for their glass surface, their glass samples that were deployed during these experiments, the amounts of particles for those size ranges were very similar for both experimental days. O'Brien and colleagues have found similar AMS, aerosol mass spectrometry spectra for the glass samples that they remained in the test house during the entire month of HomeChem and just accumulated those particles and grime from the cooking emissions. And they found that the AMS spectra for those particles is very similar to the average online AMS spectra for the entire campaign for what was present in the air, indicating that the particles that were in the air ended up on the surface and look pretty similar. So all of this leads us to think about the resulting human exposure in the indoor environment. So because particle deposition in the respiratory system is very size dependent, we can easily estimate this deposition. And assuming, of course, that a person is residing in the test kitchen where the instruments were deployed, because we didn't have personal sampling for personal exposure assessment. For a person spending the day outdoors during the home camp campaign, about 14% of the aerosol that they would be inhaling would end up in their alveolar system, alveolar section of the respiratory system. While on Thanksgiving Day, that would be about 50%. So half of the particles that they're inhaling would end up in the alveolar system. And that's because the average size distribution that you see for a 24-hour period during home camp was under 100 nanometers in size. So toxicity as well can vary according to cooking preparations. So according to this different study from Alvis and colleagues, they show that both the cancer risk shown on the left and the results from a toxicity bioassay were different for different meal preparations that they tested. And in their particular case, grilling of the pork was the worst in both cases here, both for cancer risk and the biotoxicity assay. So I'd like to spend a couple of minutes just mentioning that there are a lot of knowledge gaps related to indoor cooking particulate matter. The literature suggests that there are still questions about commonalities or differences among different cooking styles and cooking ingredients. There are questions about how ventilation could affect fate and exposure. How does it affect surface deposition, particle growth, and subsequent reactions? Does the chemical composition of the particles affect health? And by chemical composition, there's, I think, a twofold issue here. Three really. Is this composition size dependent? Is the bulk composition of the particles play a role? And then what is the influence of the absorbed compounds, as we've just seen from all those SVOCs that have their own separate health issues? Next, another issue that still needs to be discussed, even though I feel like we've been talking about this for a long time, is in terms of metrics for both exposure and health. In terms of particle number versus mass, as I showed in my talk, a lot of these, the particle mass can even be encompassed in smaller particle sizes than we're used to dealing with in an outdoor environment. And particle number can become very important when we're talking about these very small particles. And then talking about a dose versus exposure time. This is important because as you've seen from some of the results from home chem and many other studies, the time profile of these cooking emissions is very different from what's observed outdoors. You see these short-term, very high concentration emissions that happen repeatedly throughout your life. So what would be the best metric for evaluating that exposure, evaluating health effects? And then socioeconomic disparities, that's been part of the discussion today, must be mentioned as well. And finally, there are many questions that remain about the contributions of these indoor cooking activities to ambient air quality. Some things that we do know, that there's broad scientific consensus, is that for point sources of air pollution, we must control at the source the emissions. So for indoor cooking emissions in that context, what that really means is to electrify cooking, because cleaner fuels like the gaseous fuels are not necessarily clean fuels, and to use effective source control, which in the case of cooking, that means operating an externally vented, high quality range hood over the stove every time cooking activities are being performed, and or a well-positioned, properly selected portable air cleaner. And there's a whole section on this workshop about mitigation strategies. I'll finish with some acknowledgements and thank you, and I'm looking forward to the discussion.